In the Extension 2 course, we look at the motion of a particle. And really, a lot of these are just harder questions that we've dealt with in the Extension 1 course. So these are the things you can look at, and like the motion of a projectile, horizontal and vertical components of velocity and displacement, and some harder projectile problems on projectiles. So you can see that they're starting to get stuff from the Extension 1 course that are and just harder applications of it. Equations of displacement, velocity, acceleration, from simple harmonic motion, relevant formula and graphs to solve harder problems on simple harmonic motion, Newton's laws, creating equations of motion of particle in situations other than projectile or simple harmonic motion. So it's still motion, but other types of projectile motion, and describe mathematically the motion of particles in situations other than projectile motion or simple harmonic motion. So we know there's more than those types of motions, and that's where we're probably concentrating on to start off with. So this is what we're saying, like all these areas we've covered in the Extension 1 course, and we're going to do harder problems. So what we want to do is concentrate on Newton's first two laws of motion, and you physics students will understand these ones really well. So the first one basically is saying if you've got a particle and it's at rest, or if it's in some motion, unless it's compelled to change, it stays exactly the same. So it'll either stay at rest or it'll stay moving in a constant speed unless it's forced to do something by changing its acceleration. And then the second one we want to look at is the change of motion is proportional to the motive force impressed. So basically, the change of the motion is proportional to what's actually put upon it. And it's made in the direction of a right line in which that force is impressed. So there's the two ones we want to deal with to start off with. And there we also want to look at problems. And the key to these problems, we're looking at our velocity. Is it going to be in terms of x, or is it going to be in terms of t? That's the interpretation we've got to get out of the problems that we face. We need to remember this situation as well. That the derivative of a position with respect to time is the same as the acceleration of a particle of a position with respect to time is the same as the derivative of the with respect to its position of a half v squared. And remember our proof from that result that we did in Extension 2. And a lot of times we'll be working with some of these ones that not necessarily the end result, but something like v to v dx. So we'll see that in some of the problems. And our starting point for a lot of this is what the force or acceleration is doing, and namely force is mass times acceleration, which the physics students would know as Newton's second law. That's where it comes from. So let's have a look at a problem. We've got a time at mass m experiences a force. So its force there is minus mkv, and m was left out there. We want to find its velocity in terms of time, and also find it in terms of x, given that when t is equal to 0, the particle passes through the origin with a velocity of 5 meters per second. So if force is equal to mass times acceleration, and we're told the force is minus mkv, then acceleration then must be k times v. So there's our starting point. And then you can see it's a little bit different starting point than what we had in Extension 1. We either had acceleration in terms of x or an acceleration in terms of t. We didn't have to deal with one in terms of v. There's where Extension 2 comes in. It's a little bit harder. So if we start with that, we're going to look at it in these terms. Remember, we said that we can go back to these results and use any that we like. So we're going to use this one here. Acceleration can be written as dv to t to start off with, because we want to find it in terms of time. So we want to relate velocity and time somehow from this acceleration. So if dv to t is minus kt, then we can start to manipulate this. We write dv on v equals minus k times t. So all we did was take our v across there and took our dt there. So we're going to integrate both sides with respect to their variables. So integral of 1 on v would be log of v. Integral of minus k is minus kt, plus, and we're going to get a constant there. So we can then say, well, when t is equal to 0, v is equal to 5, we do that substitution. We get our constant of log is equal to 5. And then log of v is equal to minus kt plus natural log of 5. So we start to put it all together because we want v by itself. So we manipulate our algebra, get our logs together. Log of v on 5. V on 5 is equal to minus kt. And then v would equal 5 e to the minus kt. You could have looked at it this way and then integrated that way and played with it like that. Either way, you would still end up with what we have here. And that's okay. So the next part, we've done it, found our position, our velocity in terms of t. Let's find it in terms of x. So we're going to go with v to v dx this time, because again we want to relate something so we can get x in there, and that's equal to minus kv, which is our acceleration. So we've got a starting point there from that, except from the expressions that are equal to acceleration. So to v dx then, we can cancel the v's, gives us minus k. The integral there just gives us v equals minus kx plus the constant, and when t was equal to 0, x was equal to 0, and v was equal to 5. So we can write 5 is equal to minus 0 plus c, or c is equal to 5, and v then would equal minus kx plus 5. So that one was worked out really nicely. But again, it's where we start to get where we have our starting point, and makes it a little bit easier. So that's where you need to start to understand and realize, well, which one can I start with? Where can I go? So, and starts to make life a little bit easier to either get our velocity in terms of time or get our velocity in terms of x.